We're now ready to begin looking at the equilibrium constants, trying to get a little piece of information about what it is it's telling us. It's the size of the number that a chemist finds interesting, not necessarily what the number is, but how large or how small it is. It gives us an indication of what's being favored in this equilibrium. The forward reaction toward products, or is it the reverse reaction toward the initial reactants? So the magnitude of the equilibrium constant, they range from being very, very large to very, very tiny numbers. Looking at the number itself, the K constant, if we find it very large, much greater than 1, what we're saying that is that that equilibrium lies to the right. Forward reaction is being favored. We call that products. The product side is being favored. Think about what we've just said. If the equilibrium constant is products over reactants, and I have a large amount of product, I'm going to get a big number when I solve for the ratio. And the opposite is true as well. If K is quite small, the equilibrium lies to the left and the reactants are being favored. We'd say the shift is to the left, favoring the reactant side. Product over reactants, and if that reactant there in the bottom of our ratio is the large number, the equilibrium constant comes out quite small. So the magnitude of the number is what's interesting. And let's reinforce that, and this is what I'm going to call a margin note. And write this down in the margin of your notepad page. We'll write an equation, N2 plus O2 in dynamic equilibrium with two NOs. Record the Kc, and this is molarity for concentration. Kc is 1 times 10 to the negative 30th. 1 times 10 to the negative 30th. That's a whole lot of decimals in front of the number 1. What does that number mean? Well, that number is very small. The Kc is so small that the amount of product being made is negligible compared to the amount of reactants. Looking at the sheer size of this K value, very small, the equilibrium lies to the left. The reverse reaction is being favored. Sometimes you'll see me emphasize that, as I've done before, where I'll do a dinky arrow pointing to the right and a large arrow pointing to the left, indicating that reactants are being favored. So the size of the number, the magnitude, how big or how small it is of interest to the chemist. It gives us an indication. Now remember, the rates are equal, but we don't necessarily have equal concentrations. The only time that happens if K comes out exactly 1. If K is exactly 1, we have the same amount of product as we do reactant. The same number set over itself gives me a ratio of a 1. So the first part of the lesson here in this section, interpreting and working with equilibrium constants, the discussion simply talked about how large or how small the K constant is, giving us an indication if products are favored or reactants are favored. The next part of the lesson in this section really are applications of Hess's law. Now, Hess's law, originally from our thermodynamic chapter, talked about delta H, the enthalpy of reaction. Enthalpy, heat of reaction, I like that word also, exo and endothermic. Well, we're not caring about heat in this particular chapter. We're caring about the equilibrium constants, and yet really a lot of the same Hess's law rules apply when we're looking at adding equations together to find Kc's. So I'm looking at a Hess's law application, but not in terms of heat energy, in terms of K constants, either Kc's or Kp's. So the next series of slides are looking at applications to Hess's law. For instance, the direction of a chemical equation and the K constant, the equilibrium constant. If we had an original equation where A plus B goes to C plus D, just some general equation, what would the reverse reaction look like? Flip the direction. Well, we'd have reactants now, C and D, making products of A and B. If we reverse the reaction, it has a new equilibrium constant because the constant is product over reactant. What's on the right side set over what's on the left side. You flip the direction, we really are changing the K constant. So it says this new equilibrium constant is now going to be called Kc prime. The product over reactants is now the reciprocal of the original K constant. If you flip the direction, you take the reciprocal of the original K constant. We don't necessarily do this as positive and negative, as Hess's law would indicate for endo and exothermic. Now let me repeat that. Originally in Hess's law, when we use heats, delta H equal, we wrote positive for endothermic and negative for exothermic. This is very different. We're not using heats here, we're using equilibrium constants. But the idea of flipping the direction of the sign really is an application of Hess's law. If I flip the direction of an elementary equation, the K constant doesn't flip. What it does is you take the reciprocal. Products over reactants have simply flipped direction. So when I reverse a reaction, or flip the direction, if that's easier, it's the reciprocal of the original K. Write this down. In your margin, write this down. The value of Kc prime and Kc are reciprocals of each other. Kc prime is the reverse reaction. When you reverse a reaction, you take the reciprocal of the original Kc. Write that down. When you reverse a reaction, when you flip the direction, either way, you take the reciprocal of the Kc. Let's put that into practice. Let's write the equation for the formation of ammonia from its constituent elements. Kp is provided as 4.34 times 10 to the negative third power at 300 Celsius degrees. What would Kp for the reverse reaction? Well, step one, as any good chemist does, we write a balanced equation. On your paper, write with me the forward reaction, and we'll put at the end of that chemical sentence the value for Kp. The constituent elements of ammonia are molecular nitrogen and molecular hydrogen. And we see the stoichiometric ratio of 1 to 3 to 2. The Kp for this equation, the forward direction, provided for us is 4.34 times 10 to the negative third. No units on an equilibrium constant. Let's now write the reverse reaction, where molecular ammonia forms its elements, molecular nitrogen and molecular hydrogen, and that stoichiometric ratio of 2 to 1 to 3. Reverse the direction. Kp prime, all that little hyphen there, or apostrophe, whatever it looks like, Kp prime is why we read that. It's the reciprocal of the original value. When you reverse the reaction, 1 divided by Kp, and I found that, but please double check my calculator skills, 230.41. When you reverse the direction, you reciprocal the original value. Now what does that magnitude of K indicate? Write this with me as well. Write it in the same area. We already have on our paper the forward Kp value, 4.34 times 10 to the negative third. What does that number mean in terms of its magnitude, the size of the number? I think that size of the number is quite small. It's a small number, 0.00434. Very small number indicates the left side of this reaction is being favored. What's on the left side? Well, that's nitrogen and hydrogen. Look at the magnitude of the K constant from the reverse reaction, 230. Now that to me is a big number. The big number indicates the product side is being favored. But what's on the product side? Oh, it's nitrogen and hydrogen. In the forward direction, the small number indicates N's and H's are favored. And even if you flip the direction, the magnitude of the sign also changes to stay indicating the nitrogen and hydrogen. So simply reversing the direction still indicates which side is the same. It's the same thing. N's and H's are the side that's being favored in either forward or reverse. The magnitude of the K, is it large or is it small, indicating what side of the equilibrium is being favored. And by being favored, I simply mean what do we have more of in molarity units if it's concentrations, or what do we have more of in pressure units if we're looking at atmospheres for gases. So one thing we've learned so far, reverse the direction, you reciprocal the K's. Sometimes when using Hess's law, we distribute a number through the coefficients. We sometimes have to double, triple, sometimes we half an equation. If we multiply the equation by a constant, okay, and in my own words I said that means to distribute a number through the coefficients. Let's let n stand for the number we're distributing through a coefficient. If n is distributed, we change the equilibrium constant in the following way. This equilibrium constant is products over reactants, where look at those powers, they were coefficients, now we'll call them orders, are also being multiplied by the coefficient. So write this with me. Kc prime, the new K that we're solving for, looking at the reverse reaction or simply putting products over reactants. These are flipped. All right, we're looking at, I'm just trying to get my bearings. I'm going to back the slide up a moment, and I think what I've done is put A's over A and B over C and D to get Kc prime, so I took the reciprocal. I'm going to back the slide up and talk you through this. In the equation that we're looking at now, the products are C and D, the reactants are A and B. The original equilibrium constant would be product C raised to the n times C times product D raised to the n times D set over reactant A raised to the n times A and reactant B raised to the n times B. We're multiplying the coefficient. Alrighty. Then, as I put this back up, we're just looking now at the reciprocal. That's what the Kc prime is denoting. And that's just the last slide. If I reverse the reaction, we get something called Kc prime. And I distribute that through, really, all I'm doing is taking the original K constant and raising it to the power with which, oh, I'm going to back up. You're probably trying to copy that. I'm sorry, I went too fast. Kc prime is written as follows. Now, verbally, I wanted you to write product over reactant for the original value. C times D set over A times B should also be on your paper. Although I didn't type it, please include both. Product C times product D set over reactant A times reactant B. The powers with which they're raised, product C raised to n times C, product D raised to n times D, set over reactants in the same fashion. And really what's on the slide now is the reciprocal, which would represent I've reversed the direction. So you can include both, but most importantly, I wanted us to see that when we distribute through by a coefficient, we take the original K constant and raise it to that power. We don't multiply it, but it becomes the power with which it's raised. Let's write this down. In a margin, somewhere on this page, write this down. When distributing a number through the coefficients, we raise the K constant to that power. It's raised to the number you distribute through for coefficients. The original Kc raised to the power of n, where n stands for the number that you have distributed the coefficients through. Two things we've learned. Reverse the direction, K is the reciprocal. Distribute through a number through the coefficients, you raise to the power that very number. Let's try one. How does the magnitude, this probably has to turn your notepad page, doesn't it? Let me catch my notes up. Yep, top of the next page. Give it some thought, it reads. How does the magnitude of the equilibrium constant Kp for the following reaction I see 2 units of HI in dynamic equilibrium with H2 and I2. Alrighty. It has its original Kp value. How would it change if the equilibrium is now written as 6 units of HI in dynamic equilibrium with 3 units of H2 and 3 units of I2? Compare. What have we done? The original equation, a 2 to 1 to 1. The new equation, 6 to 3 to 3. What have we distributed through those coefficients? I bet you can say we've distributed a 3. Those coefficients have been tripled. Therefore, n equals 3. That original Kp value would now be cubed. The new equation where we had distributed a 3 through the coefficients to find its new Kp value, we cube the original. Notice, very important, it's not Kp times 3. You're not times 3ing, even though you did for the coefficients. You raise it to the power of 3. Whatever the number is you distribute through the coefficients, you take the original K constant and raise it to that same power. Let's take a look at this one. 2 units of NOBr is in dynamic equilibrium with 2 NOs and Br2. Notice the Kc given, 0.014. Second equation given, Br2 and Cl2 in dynamic equilibrium with 2 BrCls. Its Kc is 7.2. What if we added those two equations together? Add the equations, draw an arrow, put everything on the left side we call reactants together in a single equation. Put everything on the product side, on the right side of the arrow, as one equation. Sum the two equations. What do we get in terms of a Kc? Well, as you're writing your equation, simplify anything that's on the left and the right, just as we've done all year long. Anything that's the same on the left and right can be canceled out, just as in an algebra equation. The simplified equation is something we used to call our target when we did Hess's law. It looks like 2 units of NOBr plus Cl2 is in dynamic equilibrium with 2 NOs and 2 BrCls. When I sum the two equations, what canceled? Is it Br2s were the same on both sides and they canceled out? So I don't see them in the net equation. How do I calculate the new Kc for this sum of the equation? Well, I know we're not going to add them. It wouldn't be that easy. I sum the equations, but what do we do to the Kc's? Let's take the long way to get there once, just to kind of show how we arrive at it. Now, write this down. Everything that was on the product side, even that Br2, right? Everything on the product side from both equations. So in the first equation, it's NO in bracket squared from its coefficient times Br2. And then look down at the second equation and I see BrCl, and its coefficient of 2 means it's squared. All three products from both equations put up on the top. Do the same for the reactants. The reactant from our first equation, NOBr, raised to the second power from its coefficient of 2, times Br2 times Cl2, the two reactants from our second equation. You can clearly see how Br2 cancels. It's on top and on bottom, so it simplifies out. But what are we doing with those K constants? We're not adding. When you express them in this equilibrium value, products over reactants, see how they're being multiplied. What we've done is multiplied the two Kc values when placing both equations into the same expression. And the Br2s cancel. And what we've done, if we canceled out the Br2s, because they are indeed the same number, they'd cancel right out, we've written our target equation. NO squared times BrCl squared set over NOBr squared Cl2 product over reactants. And that indeed was our target equation. We've proven to ourselves that when we add elementary reactions together, we will multiply the K values. That's the word product here. It means to multiply. We don't add K constants, we multiply. When adding equations, multiply the K constants. 3 things we've learned. Number 1, reverse the direction, take the reciprocal of the K. Number 2, we've learned when I distribute a number through the coefficients, we raise that power, the original value of K. K raised to the power of the number you've distributed through. The third thing we've learned, when we add equations together, we multiply the K constants to find the new value for the sum of those 2 equations. Let's practice using all 3 in a Hess's law situation. Hess's law, adding together equations to find a target equation. In this chapter, we use K constants for equilibrium. Thermodynamics would have us do that for enthalpy delta H. Here's an equation. It's written down for us in our note pack. HF, aqueous, in dynamic equilibrium with its ions, hydrogen ion and fluoride ion. I see a Kc value 6.8 times 10 to the negative 4. The second elementary reaction, that's oxalic acid, H2C2O4, in dynamic equilibrium with its ions. 2 acid ions, hydrogen ions, and an oxalate, C2O4 negative 2. Its Kc 3.8 times 10 to the negative 6. Now on my slide, E negative 6 fell to the bottom line, but I think it's all right on your paper. Here's the target. When I add these 2 equations together, I want them to create the following target. 2 moles of HF plus C2O4 negative 2 in dynamic equilibrium with 2 fluorides and the oxalic acid. How can I add those 2 equations together up above to create this target? Well, let's talk through some strategy before we write anything down. For no other reason than it's written first, I always look at my first reactant in my target equation. That's 2HF. Go up into the elementary reactions and just see if you can't locate where is HF. Well, I notice it's written in the first equation, and it's the only place that it's written, so that's quite helpful. Here's what I like about it. It's on the correct side of the arrow, but I only have 1 of them. My target has 2. So I'm just predicting, I'm just brainstorming some ideas. I bet in the first elementary reaction we have to distribute a 2. That's going to give me the correct numbers of HFs. What else do we see? Well, the second reactant in the target equation is the oxalate ion, C2O4 with a minus 2. Where do you see that up above? Well, I see it in the second equation, and it's the only place I see it, so that's helpful. C2O4 with a negative 2 charge. I like how many I have, but I notice it's on the wrong side of the arrow. I bet, just predicting, just brainstorming ideas, I bet we're going to have to flip the direction for the second equation. Let's try that. Write this with me. Let's try that strategy. Let's distribute a 2 through the first elementary reaction. Write this down. 2 units of HF in dynamic equilibrium. That's going to be my equal sign. Pretend that's a forward and a reverse arrow. In dynamic equilibrium with 2 hydrogen ions and 2 fluoride ions. When I distribute a 2 through the first elementary reaction, that original Kc is now going to be squared. 6.8 times 10 to the negative 4th squared. The next thing we did in the elementary reaction number 2, we reversed the direction. Write that down in the opposite direction. Products are now reactants. 2 hydrogen ions plus the oxalate ion is now in dynamic equilibrium with oxalic acid, H2C2O4. That original Kc was written as 3.8 times 10 to the negative 6. The new Kc for the reverse reaction is its reciprocal, 1 divided by 3.8 e negative 6. Let's add the two elementary equations together, canceling out anything that simplifies. Anything cancels? Looks like the 2 hydrogen ions cancel right out of our equation. So when I add the 2 equations, we get our target. 2 HFs plus the oxalate, C2O4 negative 2. That's all that remains on the left side of both the equations when adding them together. And on the right side, I see the 2 fluorides, 2F negatives, and the H2C2O4, oxalic acid. When we add the equations together, we multiply the Kc values. So the first elementary reaction had a Kc 6.8 times 10 to the negative 4th, now squared because we've doubled our coefficients, times the reciprocal of the original Kc from elementary reaction number 2, 1 divided by 3.8 times 10 to the negative 6. When adding 2 equations together, we multiply their Kc's. Hit this. Write down your answer. Pause the video while you do. Hit it and record your answer. Let's see if we get a common answer. When I hit it, I found 0.1217. You may certainly have rounded a little differently, no problem. Remember, no units. Kc is 0.1217. Let's try another. These get easier the more we practice. I'll read it with you. Given that at 700 Kelvin units, Kp is equal to 54 for the reaction of hydrogen gas and iodine gas combining to form hydrogen iodide gas. Let's pause and turn that into a balanced chemical equation, recording its Kp. The reactant hydrogen gas, written as H2, I should put a little G so that you know it's gaseous. I didn't type it, but you certainly should add it on. Same for iodine gas, I2, as a gaseous form. My equal sign is now how I'm typing my double arrow. In dynamic equilibrium is what we'll say for that. 2 units of Hi, and that should have a little g for a gaseous form. Kp is given as 54. All right, so that becomes our first elementary reaction. Let's read on and see what it says next. It goes on to say also Kp 1.4 times 10 to the negative 4 for a reaction of hydrogen gas and nitrogen gas coming together to form ammonia gas, making ammonia from its constituent elements. We'll turn that into a balanced equation, where molecular nitrogen and molecular hydrogen form gaseous ammonia. They all have little g's for adjectives: gaseous hydrogen, nitrogen, and ammonia. 3:1:2 stoichiometric ratio. The Kp recorded is 1.4 times 10 to the negative 4th. So there's our second elementary reaction. First one, we made Hi. Second one here, we're making ammonia. How do we turn those two elementary reactions into the following? So let's keep reading. It says, determine the Kp for this reaction. Follow along in your note packet. It says, gaseous ammonia reacts with iodine gas to form gaseous hydrogen iodide and nitrogen gas at 700 Kelvin units. We need a balanced equation. We need a target. Turn those words into a balanced equation. Well, the first reactant, ammonia, NH3. Second reactant is iodine. It's molecular, I2. 2 form is our equal sign. Hydrogen iodide, based on charge, +1 -1, so we get Hi. And nitrogen gas, molecular nitrogen, N2. So the first thing we did was write a skeleton. NH3 plus I2 makes Hi and N2. And then I took some time and I balanced. I balanced with the following ratio: 2 to 3 to 6 to 1. So I just took my time and I wrote out my target equation. So here's our job. The first elementary reaction, when added to the second elementary reaction, look up above, we wrote those just a moment ago, needs to create the following target. What do we do so that when we add these together, we create this target? Now you pause the video. Strategize. What do we do to create the target? Pause, work it through, and when ready, start the video again and see if we've reached a common answer. How'd you do? Let me share what I've done, see if it matches what you've done. To the first equation, I distributed a 3 through those coefficients. I noticed that when I distribute a 3, I get the correct number of Hi. I needed that to be a 6. In the original equation, I only had 2 units of Hi. If I distribute a 3, this is what my equation becomes. I hope you wrote it down. If not, write mine with me. 3 units of H2 plus 3 units of I2 is in dynamic equilibrium with 6 moles of Hi. Notice the Kp becomes cubed. So important. It's not 54 times 3. It's 54 raised to the power of 3. When I distribute through the coefficients by a number, I raise the power. So the new Kp is 54 cubed. What do I do to the next equation? Well, I think I've just reversed the direction. I noticed that ammonia had to be on the other side from the original equation, so I simply reversed it. If you haven't written it down, do so with me now. The reverse direction. 2 units of ammonia in dynamic equilibrium with 3 hydrogens and a nitrogen molecule. Since I reversed the direction, I took the reciprocal of the original Kp, 1 divided by 1.4 times 10 to the -4th. Now when I add the 2 equations together, simplifying what cancels out, we get our target, don't we? What canceled? Well, the 3 moles of H2 simplified. And that must be it. And here's what our equation looks like then. The first elementary reaction, we distributed a 3, so I had to cube the Kp. I reversed the order of the second equation, so I took the reciprocal of the Kp. When I add the 2 equations together, it does indeed create my target. When I add the equations, I multiply the Kp's. What'd you get when you hit 54 cubed times the reciprocal of 1.4 times 10 to the -4th? 54 cubed times the reciprocal of 1.4 times 10 to the -4th. Get a very large number. Did you as well? 1.12 times 10 to the 9th. That's a billion. Very large Kp, showing the product side being favored. We say that this equilibrium is lying to the right. We have one more topic, just a little bit more to go, and we'll be ready for lesson 1. Talks about the difference between homogeneous equilibria and heterogeneous equilibria. Homo and hetero. Well, we know that every example we've worked so far in our notes dealt with the reactants and products all being in the same phase. Now what that means, they've all been gases or perhaps they've all been aqueous. If I have a reaction that's all in the same phase of matter, we call that homogeneous. Sometimes we work problems where we have different states of matter, solids, liquids, aqueous, gases, any of those other states of matter. And we'd call that hetero. So if it's homogeneous, they're all in the same phase, and we use K in terms of either concentration or pressure, depending if it's aqueous or gases can either have molarity units or they can have atmospheres for pressure. Aqueous ions can have concentration units. But typically we're just saying here that homogeneous means the same phase throughout the entire equation. But more often than not in chemistry, our reactants and products aren't necessarily all in the same phase of matter, and we look at something called a heterogeneous equilibria. It just means different. Let's say, for example, a simple dissolving process, and lead chloride probably isn't the best to use because it's insoluble. This would have to be a whole lot of stirring, maybe with some good heat. We can convince lead chloride to dissolve a little bit. Slightly soluble at best, but we get an idea here. We have a solid ionic compound, PbCl2, when placed into water. Now maybe perhaps on top of the arrow I should have typed in water to let you know I'm just simply dissolving. It's a physical process where a salt is being placed into water to create aqueous ions. On the left side, notice it's solid. On the right side, they're aqueous ions. It's a physical process of dissolving. But this would be an example of a heterogeneous equilibria. They're not all in the same phase. I have solids and I have aqueous ions. How do we go about expressing the concentration of a solid? It might actually make no sense to say, how concentrated is lead chloride solid? It's not going to exhibit a pressure. Only gases exhibit pressure, so that doesn't make sense. And if it's a pure solid, it's not having a concentration. It's like asking you how concentrated or how dilute is water. Well, water's the solvent. It would make no sense to talk about concentrated water. So here's what we're saying. Since it makes no sense for pure solids or pure liquids to have a molarity, we do not write about them in equilibrium expressions. We leave them out. How do we express the concentration of a solid? We don't. We can't. It makes no sense. You leave them out. Look at that original equation we wrote for the dissolving of lead 2 chloride, PbCl2. Its Kc, concentration, notice the bracket standing for molarity, the concentration of the lead ion to the first power times the concentration of the chloride ion to the second power, products over reactant. The reactant isn't written for, it's a pure solid. So we just see a Kc where the ions are being used. Later on, it's actually a couple of chapters away, but it's the same idea I mentioned at the beginning of our journey that equilibrium is the focus of the next 3 chapters. It's huge in chemistry, this concept of equilibrium. This technically is called the KSP. We just written one, you didn't know it. KSP stands for solubility product constant for a salt. How soluble is a salt, KSP? Coming weeks away yet, but I can see the lesson here. If we have a pure solid or a pure liquid, we do not write them in an equilibrium constant expression. Leave them out. Write this down. When I'm reading an equation, I look for the aqueous and I look for the gaseous. Those are the only states of matter that get included in Kp and in Kc expressions. If you see something in solid form or in liquid form, leave them out of the equilibrium expression. We're not saying they're not part of the chemistry, but remember K's, they're just a number, and the size of the number that we calculate gives us an indication if the forward or the reverse reaction's being favored. When we calculated K's, we leave out any pure substance. If you see an adjective, a little L for liquid, a little S for solid, do not write about them in your equilibrium constant expression. Only aqueous and gases get written for. Let's emphasize with the following example, and I'll read it for you. It says to write the equilibrium constant expression for the evaporation of water in terms of partial pressures. So that's what our NotePack example said, the evaporation of water. So I reminded us, and I just wrote it on the slide, you know, evaporation is just a phase change where liquid turns to a gas. So I just denoted the physical process of liquid water being in dynamic equilibrium with gaseous water. We could call it steam. Liquid water is in dynamic equilibrium with steam. How would we write the Kp expression? Notice it said Kp, so I do not use brackets. That would be Kc for molarity. Kp talks about partial pressure. Still the same flavor, products over reactants. But that liquid water is pure liquid. We will not write about it. The only gaseous thing in this whole expression is the steam on the product side. Kp is a direct measurement of the partial pressure of gaseous water. That capital P stands for partial pressure. I write water subscripted below it. Partial pressure of gaseous water. It's the only thing to write about for that particular equation. Let's read through another. One more example in this lesson and it will be wrapped up. Write the Kc and the Kp expressions for the decomposition of calcium carbonate. I wrote some helpful hints for you to help you kind of jog your memory of decomposition patterns. Helpful hint number 4.